Hello, I'm Zach, and we have Niall, Claire, and Tristan here today as well. And we're going to be talking to you about our presentation about a more sustainable Munich. So in our guiding principles were to create buildings that were very efficient and had sustainable energy supply, and in total creating a vibrant, attractive, inclusive community where residents could live, work, and play. And we wanted to also design for climate resilient comfort as we went through. But one of the key driving pieces here was that we had to respect the historical context and surrounding scale of Munich as we were working on our designs. And also we wanted to make this a mixed use development because that's how it is today. And so just a little bit of background on the area. We looked at the Maxvorstadt region in Munich, and this is kind of an arts and university district. It's got a lot of really beautiful buildings. Munich's also home to a lot of big industrial powerhouses and companies like BMW. The typical population in the Maxvorstadt region is students and working professionals, and the traditional energy supply comes from gas and electricity. The region has buildings generally that are from the 1950s and 60s. There are some that are from the 1800s, but for the most part, they're that old. There's about 1.5 million people in Munich, and it's a characteristic European city. As Christoph mentioned, this is kind of a study that can cross lots of boundaries in Europe as a way to retrofit existing buildings with a desire to increase density. And the neighborhood is already a very walkable place because there's a lot of transit and a lot of well-connected streets. And this makes it a really great place to be, and that's helpful in our work going forward. And as we approach this project, we wanted to focus on one protoblock, but then be able to move this out over lots of different sites in this region. And so you can see here, we have nearly 30 sites where we're able to kind of do this exact same thing over and over again. And that kind of helps us replicate this within Munich and then could be replicated elsewhere as well. And our existing protoblock here, you can see it's about 15,000 square meters in total, and it has retail first floor and then residential floors 2 through 6, and just under 1,500 occupants. But it's a very poorly performing space. The U values on the walls are very high, so it doesn't perform very well. It has old gas boiler system that's not very efficient, and it has very little daylight. So in general, it's just does not perform as we would like it to. And as we go through, we wanted to also, again, respect the Munich context. So there's regulations that we have to preserve what the facade looks like. So this is kind of the envelope we were working in, where we had to make sure from the street you wouldn't be able to see much of what we had done. And this is kind of some typical floor plans for the existing building.
So I'm going to talk about basically the 3 stages of our block design. And our ambition here was to increase the occupancy density whilst increasing the access to daylight, preserve the historical character, and try and maintain that green space in the center of the courtyard. So on the far left is the original design, and basically we got rid of the random buildings in the middle, and we put 2 floors above the perimeter buildings. And then we wanted to look at putting some density in the middle of the courtyard. So I'm going to talk a little bit about that. So this was a very simple parametric approach to the courtyard building. We went from very high density to very low density. We tried a single building and then 2 buildings, and then at the end did combinations. And the results are basically as you would expect. As you decrease the volume of the building in the middle, there's more access to light, the SDA improves, but the occupancy decreases. There's an interesting dot on that curve. That was the iteration 2.42, which you see here in this Greenspace to person chart. 2.42 was the worst with the green area per person ratio. So what we did is we went and we removed the bottom tower and replaced it with a commercial building that just a single story. And so that allowed us to decrease the density in a way that the green space to person ratio increased from 2.42 and a previous design. And then the next stage was to look at the daylighting of the perimeter building, the existing buildings. As it's a courtyard building, we don't have to worry about the heritage issues of the historical facades. And this is the original block, and you can see the SDA here is 50. And so our simulation approach was to have 4 simulation models, 1 on each facade. And the following images are going to be showing mainly the northeast and the southwest facing ones, with the 4th floor being on focus. And so these were the iterations. So on the far left, you have the original, which has a window to wall ratio of 20% and 40%. And what we did straight away was just whack that up to 90%. And then we stepped it out. That is the bottom 4 residential floors. And then finally, we added sun shelves to reflect light deeper into the floor plan. And the results from this are interesting because, so this is the annual SDA and the mean annual lux for each of these iterations. And as we increase the window to wall ratio, the SDA actually decreased because we weren't using the light particularly well. We were just having high intensity areas around the windows. So this is when the sun shelves really helped and redistributed the light from the window deeper into the floor plan, as you can see on the last 2. And then we had a little look at the visual comfort. So we're basically providing occupants with 2 blinds. One is an external one, which will cover the roof light, and that helps with mainly reducing any solar heat gains from getting passed into the glazing envelope. And then the other one is an internal blind, and you can see that once both are closed, the glare and the illuminance on that floor plan really decrease. And these internal visual renders from the 4th floor show that, again, if you close both blinds, those pink areas which are uncomfortable glare are completely removed. And then finally, after designing that, we made a few adjustments, such as pushing that ground floor commercial space back because it didn't need the light or the extra area, and reducing the window to wall ratio of the top 2 extension floors. They just didn't need that much glazing to have a good SCA. And that's our final result there on the far right in the green. We have an SDA of 68.5 in this one, which is better than that original, which was 50. So that's great. And then we're going to look at the tower design. This is interesting because it has such a range of access to daylight from top to bottom. So our approach to this was to take a midpoint, which is the 5th floor, and run simulations on that to see if we could improve, get a great SDA from it. And because this is a new building, we know exactly what the floor plan is. So we have 4 apartments centered around, at each corner around a core. And it's different to the perimeter building studies, as it has 4 facades that are open to fenestration. And this kind of presents the challenge of balancing increasing the daylight in this building and privacy, because it's surrounded by buildings where people can have views into the tower. So there's somewhere between privacy and daylight we want to land, and obviously this is going to feed into the EUI. And so here are the iterations. We just began at the beginning on the far left with 90% window to wall ratio, your classic kind of Manhattan office block, no shading, and then added shading at each iteration and changed the window to wall ratio to suit the program. And these are the initial results. You can see the mean annual lux decreases and flattens out, and the annual SEA increases slightly. But at this point, after this initial iterations, we could go into detail into the shading a bit more, and we adopted a perforated shading approach. And this basically allows us to design the static shading so that it's denser or more perforated at different points on the facade depending on the need for light. And we designed this with a solar heat gain control in mind. So this is the energy loads for that tower, the cooling and the heating. And there's a switchover point at the end of May in Munich for the tower, and it switches back at the beginning of October. So that period between the end of May and the beginning of October is a cooling period during the summer, and then the rest of the year is a heating period. So during the heating period, we want as much light as possible, really, in the building. And then during the cooling months, cooling period, you want shade. And that's exactly what we did with our design. And you can see this once we scale up to the full tower, how in the summer you have a dark facade from the shading, and the winter you have a light facade from the sun getting in. And if we look at the floor plans, the story remains the same, where we have these light yellow and orange spots, more so in the winter, and then that changes into a darker floor plan in summer, which is great. And this is the final results after all those adjustments. And so we managed to get an SEA of 82 from that single floor, which basically doubled from the original 90% window to wall ratio with no shading. So that's great. And you can see with this question of balancing privacy and daylight, the static shading system that we're implementing actually really helps with preventing people from looking into someone's living room or bedroom. And this is just showing the section from the original buildings on site to what we're proposing. So you can see the top two new floors on the perimeter buildings. You can see the new facade design with the stepped courtyard facades. You see the new tower, and all of this improved the SDA whilst retaining that really nice green courtyard space in the middle. And just to zoom in on the retrofit of the block, we're basically going to improve the building fabric by having low U values for the walls, the floors, the roofs, and the glazing. We're implementing a heat pump with a high coefficient of performance. And as you've seen, we've increased the window to wall ratios so that our SDA has improved massively, whilst retaining that historical street side facade. And then this has all allowed us to increase the density by 23% to around 1,800 occupants.
Right, so here you can see the difference in daylight availability between our existing and retrofit buildings. As a result of our extensive daylighting and shading studies, our retrofit has a much higher SDA than the existing, going from an average of 8 to an average of 68. Also, the UI has drastically decreased in our retrofit buildings for both the residential and retail. This is partly because we have significantly reduced heating and especially lighting loads, so that for residential spaces, the UI decreased by 71% and the retail is down 44%. We also wanted to explore how the changing climate would affect our protoblock in the future. So the retrofit performs better in 2020 and for the next 15 and 45 years. The main reason that this retrofit doesn't perform even better than it could have is because with this warmer climate, while the heating loads in the winter are reduced because you just don't have to heat as much when it's warmer, the summers will be even hotter because of that. So we have to put in air conditioning, and so we'll thus have a higher cooling load. And so then continuing with that, looking at our carbon emissions over time, we comparing between our existing and retrofit. So while the retrofit has a higher initial bump in embodied energy because we have building costs because we are adding to our protoblock. For the existing, this is a scenario where we're not building anything, so there is no initial bump, but the existing does have a much higher UI, and so it quickly surpasses the retrofit scenario, in carbon emissions, and after 60 years, there would be a 63% decrease in total carbon emissions. And so we also wanted to look at 3 potential energy systems. And so we compared how they were effective in carbon emissions and financial costs. So the baseline is how it exists right now with grid energy and using gas boilers. The all-electric scenario powers everything using electricity, and the gas trigen uses heat from a cogeneration plant to produce heating, electricity, and cooling. However, this scenario still has a lot of carbon emissions, so we decided that electric was our best option. And so we looked into producing electricity with PV. And so for this, we had PV cells covering about 80% of the roofs of our buildings, which would supply 87% of total electricity demand. And so you can see here in the summer months, we would actually produce extra electricity that we could potentially sell back to the grid.
So we were unable to run the Harvest plugin, but we wanted to illustrate one of the key benefits of providing on-site controlled environment farms. Ideally, this would inform people of the carbon impacts relating to their current diet and provide incentives to change their eating habits with cheaper, locally sourced plant-based sustenance. The 2 charts on the first slide show the average daily consumption in calories and GHG emissions for a standard German diet. And animal products 74% produce 74% of the GHGs, while only making up 30% of someone's diet. So we replace these with high protein plant equivalents such as nuts, soy, and pulses. This chart shows that if someone was to remove all meat from their diet, they would dramatically reduce their GHG footprint. If all the inhabitants of our block moved to the diet, annual GHG emissions would be cut up to or by 5,800 tons of CO2 equivalent. Future studies could investigate how many of the vegetables can grow locally and how this would reduce the cost of certain vegetables, but ideally, on-site farming would help aid this transition to a plant-based diet. And the urban mobility, or the urban thermal comfort, this was to show, compared to the original block and the proto block, how much the Courtyard's outdoor comfort enhanced. So the original proto block, for 1 point of interest over the year, had 28% of the time hitting a thermal comfort that was not stressful for a person. For the same point in the new iteration, which is the proto block, it showed that 43% of the year in this one specific spot would be thermally comfort with our new design. Urban mobility, we didn't need to change much here. The block is already an established place with about 1,616 amenities within an 800-meter radius of the block, which is something that is a comfortable walking distance. So we didn't need to add any additional amenities as it has already organically grown in the area.
And kind of in summary, we wanted to talk a little bit about the financial performance of this block. We've improved our SDA over 50%, and so we can now have a 6% rent premium, which is great. And just in the existing apartments alone, that's worth 74,000 euros a month in additional rent. We've added all of this square footage of extra residential space. That's another 300,000 euro a month in rent. And the total rental income has gone up, so 380,000 euro a month, which is a 30% increase. And just in conclusion now, we've added 500 square meters of retail space. We've added 1,200 square meters of residential space, and we've increased the occupancy by 23%, all while maintaining the historical facade. And again, to each of our key metrics, we've improved daylighting 750%. If everyone in our block changed their diets, we could get 80% greenhouse gas emissions reductions from food. We are decreasing the total emissions by 63% by 2080. By our upgrades, the neighborhood's very walkable with a score of 78. We've decreased our EUI 68%, and our outdoor thermal comforts increased 15%. Additionally, using on-site PV, we can reach 87% of our total energy consumption from on-site production, and our financials are, we're getting €380,000 more a month. Thank you.